Welcome to lesson 3 of industrial automation and control. In this lesson, which is entitled energy savings with variable speed drives, we are going to explain and demonstrate that for a kind of application which is very predominant in the industry, very common, how firstly we are going to see what are the various kinds of flow control applications. That is the application that we are trying to consider. So, flow can be of gas or liquid. So, accordingly we have either what are known as fans or blowers, or we have pumps. Fans, blowers and pumps constitute an enormous a very significant fraction of the loads which are driven by motors, and motors which consume a large amount of electrical power in the industry. So, they are very common applications and very significant from the energy point of view. So, we are going to see that in such applications how flow is to be controlled, and then we are also going to see that if flow is typically controlled by driving a pump by a motor, but if you drive a pump by a motor, then it will drive a certain amount of air, let us say. If you have a pump, it could be water. Now, the demand for this air or water is not the same all the time. So, the flow has to be controlled. Now, so firstly, how do we, when we connect a machine to the pump, what is the amount of flow that is established? That depends on the pump characteristics, that depends on the machine characteristics. So, we are going to see that how when you connect a pump or a fan with a so called load, how is the operating point established, what will be the pressure, what will be the flow. It is actually much like establishing an operating point when you connect a battery with a circuit or a load, right. So, we are going to see that, and we will see that depending on how we can vary this operating point. See, we have to vary this operating point because we need to vary the flow. Now, the flow can be varied by various ways of varying the operating point, and it is so some of these ways are maybe very simple, but may not be efficient from an energy point of view, while others may involve more complex technology, but possibly would be more energy saving. So, we are going to look at two of the most common techniques and show that how their energy characteristics are going to be different. In fact, that will motivate the next few lessons in this course that we are going to have on industrial drives. Probably this lesson would show why industrial drives are, show at least one side of the story, that why variable speed drives are such an important thing, such an important technology in industrial automation and control. So finally, we would also see in the course of discussion that when to choose what type of flow control or drive, right. It is not that you always energy saving is the all important criterion. So we will discuss a little bit on that. So let us look at a basic characteristic of a fan, right. So here we are, the fan is this is the intrinsic characteristic of the fan itself, irrespective of what the load is. So the fan actually develops a pressure at its outlet and also develops a certain flow, and this it develops when the fan is rotated at a certain speed. So when we have plotted this curve, which is whose one axis is flow and the other axis is pressure. So it shows the pressure is somewhat like voltage and flow is somewhat like current. So in that sense it is like, since we are many of us are electrical engineers, so this is somewhat like a VI characteristics of a battery or an energy source. And we must remember that this curve is drawn at some speed, at a given speed. Of rotation. So if the speed of rotation is changed, then this characteristic will shift up and down. Actually you will get a family of characteristics with decreasing speed, right. So this is the characteristics of the fan as such. Now if this fan is now connected to a load, right, the load means that it could be various things. For example, typically fans are used in furnaces. So in the furnace, typically if you go to a power station, you will find that you have big boilers, and these boilers are heated by furnaces, and these furnaces have two huge fans. One is called an induced draft fan, another is called a forced draft fan. So these are like, I mean, a furnace is like a chula. So you need to blow air into it for combustion. So these fans actually blow that air, and the induced draft fan actually sucks out the after combustion air, most full of carbon dioxide. So these are so it is the furnace which is the load. So if you connect the fan to the furnace, then at a certain speed of the fan, a certain operating point or a certain pressure flow will be established. So basically, how do we get that? So this is a fan characteristics which will come back to a little later. This is a little complicated. Actually, basically, okay, let's have a look at it. Basically what is being done is that this actually gives a family of curves, right. So on this axis you have this CFM, means cubic feet, which is an unit of volume per minute. So this is nothing but volume flow rate. So this axis is Q, right, and this is total pressure in inches of water column, right. So basically this is pressure or P. Now so you see part of the fan characteristic is shown, and you can see that a family of curves are shown. So what are these family of curves? So basically the various operating points, for example, these are, if you see these constant lines, I will draw it here. So for example, this line, it starts with this number 500, and here it is written RPM. So which means that this is the, if the fan is made to rotate at 500 RPM, then the pressure flow characteristic follows this curve. Similarly, you have a family of curves for various speeds. On the other hand, look at these dotted lines. So this dotted line, it says 150. So these are constant horsepower lines. So these are constant horsepower lines. So if you operate it along this curve, then you always spend 150 horsepower. Similarly, you have a number of curves, right. Similarly, you can have efficiency, constant efficiency characteristics. Say this is 70% line, this is the 80% line, and so on. So basically this curve shows that if the fan is operated at various speeds, what are going to, so basically pressure flow characteristics with something constant, either the speed is constant or the energy is constant, so that you can conveniently find operating points. And in fact we will use this curve later on to find out, to actually compute the energy savings, right. So having understood this, let us move on, and we will come back to this curve in a while. Yes. So here now we come back to how an operating point is established. So you see, just like, remember that when we computed operating points in our circuits courses, we drew what is known as a load line, right. So on the other hand, you have a load has a certain characteristic, means that if you want to create a certain amount of flow through that load, in this case maybe through the furnace, you need to create a certain amount of pressure difference, right. Suppose you take a pipe, then to be able to create a certain amount of flow through the pipe, you need to create a certain amount of pressure difference across the two ends of the pipe. So that is the characteristic of the pipe, that to create a given amount of flow, how much pressure difference is needed. And typically it turns out that it follows a square law. Basically that occurs because of Bernoulli flows when you have what is known as turbulent flow. That means when the flow velocity is high, then there is a law called Bernoulli's law, which we are not going to now, from which you can derive that the pressure flow relationships through any constriction, if the flow velocity is sufficiently high, that is if the Reynolds number is so high that the flow can be called turbulent, then typically the pressure flow relationship is quadratic. So the load typically follows such an equation with some constant k. So if it is a narrow constriction, this value of k is going to be high. If it is an open constriction, value of k is going to be low, and so on. So if you connect such a load across the pump, then they will intersect, and this is the operating point. So this is the operating point. So immediately if you connect, this is the flow and this is the pressure which are going to be established. So the pressure which will be established, if you connect this pump with this load, this flow will be established and this pressure will be established, right. So now let us talk about varying the flow, because we need to, depending on the load characteristics, for example, if your electrical energy demand decreases, then you need to reduce the rate of combustion. So you need to reduce the flow, air flow into the furnace, right. So how do you do that? So typically it happens, this is a typical case. We are calling it a system load profile, which means that the system to which we have connected the load, what do you mean by the load? We mean by the load we mean flow rate. So you see that this is the demand, a typical demand profile. So it says that this is, let us say that this is the maximum flow is 100, that can occur, that we are calling 100%. So since we must have kept some amount of safety margin, so probably maximum flow hardly ever occurs, maybe it does not occur at all, or maybe occurs for a very small time. So most of the time, that is, the flow is actually between, you see, about 45 to 70%. So this maximum time the flow stays within 45 to 70% of the design flow range. Similarly, it stays at it stays between 40 and 45% for, so that is about 11 point something this percent of the time. So 1, 2, 3, 4, 5, so about more than 50% of the time it stays within this flow range, and similarly it stays within 25 to 30% for 1% of time and 30 to 35% about 4% of time, and so on. So this basically shows that in the of the total operational time, let us say a day, what is the loading? If you take a loading of say 40 to 45 or 50 to 50, a particular loading level, for how much does it stay? What percent of the time? So there are some things which are important to note here. Firstly, note that the fan size must be selected based on the 100% consideration. So because the fan, for however small time the 100% demand comes, if you select the equipment such that that demand will be met, then the fan size will be selected by the 100%, but most of the time it will not operate at that level. So rather it will operate most of the time at half level, and it will also operate at very low levels for a very small amount of time. So this is a typical load characteristic. Now let us see what happens. So we need to shift this operating point, right, all the time. So let us see now what happens if we shift the operating points. So this is summarized. So it says that this is like roughly, suppose, because we are going to see an example. So suppose in our example 100% CFM means again basically flow, cubic feet per minute. This is CFM means Q. So 100% flow stays for 10% of the time, 80% flow stays for 40% of the time, 60% for 40% of the time, and 40% 10% of the time. Imagine such a case, okay? Then now let us see that what are the various ways of controlling. One of the easiest way of controlling a airflow is to switch on and switch off a fan. This happens regularly. If you see a home air conditioner, you must have noticed that the fan, in that case the compressor switches on and off, right? So it's a kind of on off control. So in a similar way, if you want to control flow, then you can also switch off and switch on the fan. So what will happen if you do that? So you see, if you switch on the fan, suppose the flow rate will rise for a little time, then it will fall again, and then you will switch it on and then switch it off. So you will be able to establish an average flow, and this average will actually depend on what is known as the duty ratio. So this is on, this is off. So basically the average value will be or rather actually what will happen is that if you it will not rise slowly because the time constant will be fast enough, rather it will be like this. So for the moment you switch it on, some flow will be established. The moment you switch it off, that flow will fall. This is an approximation. Actually the flow will rise fast and it will fall fast. So if you approximate it as a square wave, so again if you switch it on and switch it off, so basically if this is the flow rate Q max, then the average flow rate will be given by Q max into T on by T on plus T off. This is very easy to know. This is T on and this is T off. So the average flow you can change by simply increasing T on, by simply changing T on and T off. Okay, this is probably the simplest way. You need nothing. You only need the motor and the fan. You anyway need, but as far as equipment for driving the motor is concerned, you need nothing. You just need to switch on the motor and switch off the motor at a certain frequency or certain rate. For that also you need some equipment, but that is very simple. But this is hardly ever used because of the fact that there will be flow pulsations, and these kind of fans are typically used for industrial processes. We use them for cooling, for things like combustion. So what will happen in the furnace, for some time suddenly lot of air will come. So when a lot of air will come, if there is, see, what we want to do is we are giving fuel and we are giving air. So to get the maximum thermal efficiency from the fuel, we need to have a fuel air ratio, perfect fuel air ratio, such that full combustion of the fuel will take place. So if you put more air, then also air is wasted, and if you put less air, then the fuel will not burn. So in other words, that pulsating value of flow is not good for combustion flow control. So similarly, another major application for flow control is for cooling. So it is not good to, so if you sometimes if you send coolant and sometimes if you do not send it, then the temperature on the equipment will be pulsating, and this temperature may affect reaction rates, it may cause thermal stress on the equipment. So in general, for industrial flow control problems, we cannot tolerate such pulsations. So therefore this on off control method is not good. So we go for other methods. So what are the other methods? So another very simple method is, so on off control is the simplest of control. There is going to be temperature fluctuation. Basically flow fluctuation may cause temperature fluctuation. Sometimes for home applications it is used when you have less load and you have a large volume. So if you so there is a lot of thermal capacitance, so little bit of flow variation will not be felt because of large volumes of room. So I mean sometimes for home applications, ventilation, HVAC applications, this kind of control is used, but generally not used industrially. The next control which is used is called the outlet damper control for the fan. So outlet damper means, basically a damper means it's like a set of vanes, just like this, sometimes on the you must have seen what are those called? They're when you put something on the windows to keep out the sun. So there you can change gaps. You can move them. Either you can keep them like this, or you can keep them like this, so that some air can flow. So basically dampers are also similar things. So what you do is you put a damper at the outlet of the fan. So basically the damper puts a resistance and does not allow air to flow clearly. So by that you try to reduce the flow. That is a very, it's a relatively simple method of flow control, because the controls required for creating a particular resistance in the damper or creating a particular damper angle is actually very simple. But what is the third method? The third method, and which is the very energy saving method, is variable speed fan control. So you don't put any damper, but you rather change the speed of the fan and reduce it when you require less flow. But for that you require a variable speed drive of the motor, and that is much more sophisticated technology is required, especially when the motor is large, compared to dampers or valves. But as we shall see that they can save considerable amount of energies. So let's see. So now let's look at what happens to the operating characteristics when you have damper control. So here is the fan curve. You can see that. Now a damper is essentially actually puts a resistance. So basically we had this. So you can consider the damper to be part of the load. So as you are closing the damper, this load characteristic of P equal to kq square, this k value is gradually increasing, which means that as the damper is closing, more and more pressure is required to drive a given flow. That is natural. So, as the damper is closing, this curve is shifting this way, because this is increasing k. Now, what is happening to the energy? The energy in a fan, the energy being delivered is P into Q. So, in other words, it is the area of this rectangle at any operating point. At this operating point, it is the area of this rectangle. This is the area. When you are at this operating point number 2, then this is the, actually I could have taken a different color. Okay, let me take this color. So, at the other operating point, this is the, and when you take the third operating point, which is this, then this is the area, energy demand. Okay. So, you can very well see that what is the difference, how if you move from this operating point to this operating point, what is the difference in energy? The difference in energy is actually, this part is common, this part is common between them. Can you see that? So, this is common. So, this is gone. On the other hand, this is gone and this is added. So, the energy saving is actually comes down to the difference between this area A1 and this area A2, which is very low. So, you see that even if you have moved from this operating point, you have come from 100% to 80% flow, the energy has not fallen by that much amount. The energy has fallen only by the amount of difference between these two areas, right. In fact, the same, so the energy fall is not so much. So, in fact, if you can see the energy curve, so you see that in damper control, as you are going from 100 to 80, the energy fall is only this much, very low. So, you have, so there is a 20% flow reduction, but there is probably a 5% energy reduction, power reduction. This is not pressure, this is power, this is wrong. Okay. So, that is why this method is not so energy efficient. You are not saving energy, flow is reducing, but you are not flowing energy. But it is a very simple method, you do not require much, you require either a valve or a damper, and you close and open it. Now, what happens if you do a variable speed drive? Now this is that particular case. So, if you want to see this, we can come to, we can let us come to the, if you want to see this figure. So, what does it say? It says that for our example and for the fan curve that we have seen, if you take 100% CFM, 100% flow, the horsepower requirement becomes 35. We will see how it comes to 35 from those curves. If you have 80%, the horsepower requirement is also 35, hardly any reduction. If you have 60%, it falls to 31, if you have 40%, it falls to 27. And from the load characteristics, we have seen that 100% load stays 10% time. So, per hour, percent is 3.5 is the weighted horsepower. Oops. So 35 horsepower level stays 10% of the time. So therefore weighted horsepower is 3.5. We are trying to calculate the average horsepower, right. Similarly 35%, again 35 stays 40% of the time, that is 14, then 31 stays 40% of the time, that is 12.4, and 27 stays 10% of the time, that is 2.7. So the average horsepower requirement is 32.6. Remember this figure. We will come back and see that if you do a variable speed drive, what for the same pump and for the same load profile, if we had a variable speed drive, what would have been this figure. So we have a 32.6 horsepower average horsepower requirement for the load and the pump, right. So just we would also like to see how these 35, 35 and 31 figures are located, because otherwise you may not believe me. So let us go back and oops, okay. How do we close this? Okay, can I go back to the so I am going back to the fan curve just to show you, alright. Yeah, so we are at the fan curve. So let us see that actually this has been calculated with a fan RPM of about 300. So this is the 300 curve. So we are looking at this curve. This is the constant RPM 300 curve, okay, and we are at 100%, okay. So this is somewhere over here. So you see that it is somewhere over here. Can you see that? So it is somewhere over here, okay. Now you see what is the power requirement here. Look at these curves. This is 30. This is the constant 30 curve. This is the constant 40 curve, 40 horsepower. So where are we? We are at 35. Now what happens when you are 80% flow? That is when you are here. So when you are here, you are roughly here. So you are at 80% curve. Now you see that where are you? This curve and this curve are moving in parallel. So if it is 35 here, it is going to be 35 here also. That is why this is also 35. This is also 35. If you do 60%, that is here. Where are you? You are 60% would be somewhere over here. Yeah, so you are here. So that is a little reduced. You see, this is the 30 curve, this is the 40 curve, this is the 40 curve. So therefore, and it is actually a nonlinear variation, because 50 to 60, 60 to 70 it is gradually getting closer. So this is something like 31, 32, it is slightly reduced actually. So this is how you get those figures from an actual pump characteristics, okay. So now we go forward quickly again and go on to the variable speed drive case and see what happens, right. So that is the case. Now here, before we discuss that, we need to understand what are known as the fan laws. So what are the fan laws? The fan laws say that in a fan, roughly Q2 by Q1 equal to N2 by N1. If you change the speed, the curve shifts in such a manner that on the Q axis you are going to get proportional these things. and P2 by P1 equal to N2 by N1 square. So, the horsepower variations are going to be N2 by going to vary as N2 by N1 cube. So similarly, so if you know this Q2 by Q1 and you know P1, you can calculate P2 by this formula, because P2 by P1 equal to Q2 by Q1 whole square. If you eliminate n from these two, then you get basically P2 by Q2 square equal to P1 by Q1 square, right. So, P2 by Q2 square is equal to P1 by Q1 square. This is at speed n2 and these two are at speed n2 and these two are at speed n1. Okay. So, now having known that, we come back right. So, we see this variable speed fan control. So, now what happens is that if you want to reduce the speed, we are not going to put any damper or any valve. In other words, the characteristic of the system remains unchanged. Now, we are changing the speed of the fan. So, the fan characteristic shifts. So, this is, let us say N1, this is N2 and this is N3, and N1 is greater than N2 is greater than N3. Okay. So, now what happens is that now the operating point will change along this. This is the first one, then this is the second one, and this is the third one. So, what happens to the power requirements now? So, the power requirement for the last one is this. See, previously as we were reducing flow, pressure was going up. So, the power was not falling. Now, as we are reducing the speed, it is not just that the flow is reducing, it is the pressure is also falling, right, and very rapidly too. So, what happens? So, this is the area required, this is the energy, and similarly for this case, second operating point, this is the energy, and for the third operating point, this is the energy. So, for the third operating point, this is the energy. So, you can very well understand that energy falls very sharply. So, that is why you are going to get a huge benefit in terms of energy savings, right. So, you can now see that the power curve, how sharply it falls compared to what you had seen in the case of the outlet damper control. So, this is the essence of energy. So, this shows that how energy saving variable speed drive can be, and just to drive the point home, we are going to show you that we are just applying that same formula that what happens is that, remember that at Q1 equal to 100, we had a HP requirement of 35 HP. So, with Q1 equal to 80, Q2 equal to 80, HP requirement will be 35 into 0.8 whole cube, which is equal to 35 into 0.512, which is almost equal to 18 horsepower. So, this is 18. Similarly, if you multiply this by 0.6 whole cube, then you will get 7.56, similarly 2.24. So, these are the horsepower requirements now, applying the fan laws, and you can get very similar figures if you see the fan curves, because the fan curves obey the fan laws, right. So, here we are. So, now let us see the energy average horsepower requirements when you are varying the speed. The 100% case is the same, 33.5. The 80% case is now totally different. This was 35, remember, this was 31 and this was 27. So, now the average horsepower requirement is 32, where the previous one 13, the previous one was some 32 point something. So, you can imagine that what amount of power saving has been achieved, almost 20 horsepower, which is 1400 kilowatts, right. 14,000. So, yeah. So, this is this is a little calculation. This is this dollar figure is because of the source from which this is taken, but this turns out to be almost equivalent to hours. If you take about 45 rupees per dollar, so this becomes about 2.5 rupees, which is a kind of an average rate. Not exactly, it varies from state to state, it varies on various energy slabs, and industrial energy rates are anyway not just depends on the kilowatt, it also depends on the maximum demand. So, approximately speaking, if you take 2.5 rupees and if you take 2.5 rupees here, then you can inquire roughly you have a 10,000 kilowatt hour per month. 10,000 kilowatt hour per month saving at 2.5 rupees per kilowatt hour, that comes to be a 25,000 rupees saving per month on a single fan. Now, the question is whether this is justified. So, whether it is justified will depend on, see, apart from the conservational aspect of energy, that we need to be energy efficient, we need to because fossil fuel is not going to last forever, etc., etc. If you ignore those things, then people are going to look at money. So, if you it all depends on it, it's again remember that in the early lessons of the course we talked about capital cost and we talked about variable cost. So, energy is variable cost. So, whether people are going to resort to simple damper type of control, or whether they will actually buy these variable speed drives, depends on how much money is required to buy these drives and how much money is required to maintain them against how much savings these drives give. So, it is all basically because of these comparative figures which will decide practically speaking whether a particular industry is going to adopt this technology or the other. Now, it so happens that why the outlet damper technology was more common is because the variable speed drive technology was not so developed, it was not so robust, so it was way too expensive. So, therefore, people always opted, even if they were not energy efficient, people opted for this damper and valve control kind of techniques. But now with these variable speed drives really becoming robust and cost effective, it shows that it makes a lot of sense to acquire variable speed drives for such equipment. Okay. So, basically it is the cost and it is the capital cost of purchasing the equipment and the cost of maintenance which decide whether these technologies are going to be adapted, right. So, you see this shows that how important it is to make a technology cheap and to make a technology robust, right, otherwise it is not going to be adopted. So, we move over to the case of pumps. For pumps, this is a pump characteristic, again the same thing, basically same thing. So, we are going to do this a little bit fast. So, this is the pump characteristic and this is the system curve, which is again of course there is a little difference in the sense that fans drive gases which are compressible and pumps drive liquids which are generally incompressible. So, there is a slight difference there, but it looks essentially the principle is all the same. This side you have total head in feet of water, right, Previously you had inches because that was gas, this is liquid, and you have this is given in you have to choose a unit because this is from an American reference. So, this is gallons per minute. So, similar to the fan characteristic, you can have a pump characteristic where again you have the pressure up. I made a mistake. How do we go back now? We don't have. Oops. Okay, so this is going to be tricky now. Oops, I can do this. Yeah. So, yep. So again, you have this pressure, and this side you have flow, and this side you have various RPM. You see that. So you have these constant horsepower lines and the various speeds also. So you see that there are these constant, these lines are these various speed lines, and these dotted lines as before are these dotted lines are the constant power lines. So it's like the old curve itself. Okay, so again in this case, in the case of fans you put dampers, in the case of pumps you put valves, right, flow control valves, which we have already seen in our earlier lesson. So that kind of, when you close the valve, it's generally called throttling, right. So this shows how the operating point shifts if you have one system which is open, another system which is throttled. So again you see that the load curve changes and the operating points will shift from this to this, right. So the same thing happens here again for pumps. This is a variable speed pump control. So you have a constant speed drive. One way of controlling is either you have a constant speed motor drive and you have a valve, or you have a variable speed drive of the pump, depending on the feedback, depending on the load. Basically that drive has to be controlled and some speed reference has to be given. We will see in our future lectures as in detail as to how the speed of a motor and a pump can be controlled. Oops. Okay, next. Now, if we control the speed as before, the pump characteristic will now come down. This is N1, this is N2, and N1 is greater than N2. So the operating points will now shift from this to this, okay, just like previous case. So if you do a similar analysis on this pump, a similar thing comes out, that is, see, at 1200 the head requirement is, and the BHP requirement is 25. At 960 for throttling it is 23, hardly reduced, but for variable speed drive it is much more reduced, again because of the fan and the pump laws, okay. So a similar saving will result, that is what. So we come back. So this is just another depiction that if you have it shows that if you had a throttling method, then the energy would have fallen along this path. If you have variable speed method, it will fall along this path. So this is the energy saving that you are getting, right, or rather these at any load, this is the energy saving that you are getting. There is a difference between these two, which is substantial. So only thing is that in the case of the pump, there is sometimes pumps operate with a static head. So, if you have a static head, then the load characteristic can be, this is one without static head, where P is equal to kq square type of characteristic, but a pump can also operate with a static head where the characteristic is P equal to k1 q square plus k2. So, this k2 is the static pressure which is there at the pump inlet. Sometimes the pump may be elevated, you know. So, in such a case it has a for example, the load, the pump may be below and the load may be at a vertical height. So, even if there is no flow, there is always a constant pressure on the pump. Okay. So, for driving such loads, as we shall see, that the energy saving is reduced. So, it turns out that with static head, this is the throttling method. So, and this is the variable speed drive method with no head. Okay. This is for 31% head, this is with 63% head. So, as the head increases, the energy saving actually reduces and moves towards the throttling method. Anyway, those are fine points. So, we have, what we have done in this lesson is that we have seen the fan and the pump characteristics, we have seen the load characteristics and typical load profiles, and we have seen two kinds of control, for fans outlet damper and for pumps throttling control, and for pumps and fans we have seen the variable speed control, and we have seen the energy characteristics of these control schemes, and we have got an idea of the energy savings, right. So, here are a few questions for you. Why is it that typically load requirements are stated in terms of flow rates? Why? You have to look at the applications, and we have discussed this. Why is it that load requirements are generally shown as parabolic pressure flow characteristics? Again. And third is that from these characteristics, it will be interesting if you can find how the efficiency varies. Does it increase? Does it decrease as flow is reduced? So, these are a few questions on which you can ponder, and thank you very much. Welcome to lesson number 32 of the course on industrial automation and control. In this lesson, we will mainly be looking at, not mainly, solely be looking at DC motor drives. Now, we have seen that actually drives are very important components of automation, because they create motion, and creating motion is extremely important for industrial operations, both in the process industry as well as in the manufacturing industry. For example, if you take the manufacturing industry, then you need, see, the whole of manufacturing operation, we have done in the previous lectures some given you some exposure to CNC machines, which are various kinds of metal cutting machines. You have seen that very precise motion is to be created in those machines. Either the block or the tool, either the job or the tool have to be moved in precisely from one coordinate to the other. So, that is one kind of example. Then there is a big example of material handling. So, all material handling devices require you to create motion. Similarly, in the process industry, you require pumps which will create flow, you require control valves. So, for their operation also you need to create motion. So, creating of motions is very important. So, we are, in most cases, motion is generally rotational motion is created by a motor, because it is very convenient. In a small space you can create that motion, and then using various kinds of mechanisms, this motion is converted into various other kinds of motions like linear motions, etc. So, we are going to look at basically creation of rotational motion using motors, and we start with DC motors, because they are still widely used and they are the simplest kinds of motors which are used to create motion, and lot of application was there. Now some of the applications are being replaced by AC motor drives, but still a lot of them exist, and it is a proper point to start the discussion on drives. So, in this we will mainly be considering, we have an introduction like we are having now, and then we will look at two kinds of, we are basically in this lesson we are basically going to see what is the technology, how exactly, what is the engineering of these drives, how exactly these motors are rotated, sometimes they are accelerated, sometimes they have to be decelerated, they have to stop, start, they have to move clockwise, counterclockwise. So, how all these motions are basically created, the technology part of it, not the analysis part of it. You have already seen some part of analysis of DC motor control in the context of a CNC machine in a previous lesson. So, in this lesson we are mainly concerned with seeing how in a motor you can create various kinds of motion. So, we look at two kinds of this creation of motion, since these are electric motors. So, they require various kinds of electronics, power electronic devices and circuits. So, we are going to look at two broad classes of circuits. One are line frequency converters and switch mode DC-DC converters, which will show you two different ways of controlling DC motors. So, having said that, let us look at the main instructional objectives of this course. So, after learning the lesson, the student should be able to describe the main features of a DC motor, basically should be able to understand how it works, then should be able to draw block diagrams of various DC motor control loops to be able to identify how the DC motor is excited, how feedback is obtained, etc. And then they will be able to explain the basic ways in which a line frequency controlled, basically line frequency AC to DC converters, for how they are used for DC motor control. And finally, they will also understand the accept of a, there is a concept of 4-quadrant operation of motors. So, that is very important in for drives to understand. Then lastly, they will be able to explain the operation of a switch mode DC-DC converter based DC motor control.